Pilot's getting smaller, rate the magnitudes of basically the change in magnetic flux with respect to time.
So wouldn't these be the same at this point in time, because they're both be zero, because they both have the same flux, which is constant?
No, but at that moment in time, it's getting smaller, so it's not constant.
But if it's just talking about the area enclosed here, then I don't understand why there wouldn't be a change in flux there.
No, that's, so we've got, right, so, all right. So my flux, B dot dA. I know my B is not changing with respect to area. It's changing with respect to time, but not area, so this is a constant with respect to area. This is my magnetic flux. I will make my area vector the same direction as my magnetic field, so I'm not gonna worry about the sign there. So this is just basically B times the integral of dA, which is just BA. My integral of E dot ds is just the EMF, which is negative d phi b dt, Faraday-Lenz's law. I'll only worry about, I think I ranked the magnitude, so don't worry about the negative sign. So I've got d B dot A dt. So what I care about is the magnetic flux. If I, oops, that should just be BA in this case.
Sorry, is it BA because the field is constant?
It's BA, well, one, because the field is constant, and two, I made the area vector, it's gotta be perpendicular to the surface, and so I made it the same direction as the magnetic field.
Okay.
Well, my areas of each one is separate, so D is like that, that's the area of it. I think C, B, and A. Those areas are not changing.
No.
So A is a constant, so it comes out. That's the same for all of them. So it really is a matter of the area that has a magnetic field going through it. And I think the magnetic field,
It's right outside of the second line there. But I guess I'm not understanding how the flux is changing on the inner ones if they're completely engulfed in the magnetic field.
no, there is a magnetic field. Why?
Isn't that what the purple is?
The purple is the magnetic field.
So how would the flux be changing on the inner two if they're completely engulfed in the field?
Because the field itself is changing. Magnetic field's getting smaller, it's shrinking.
So now, if this stayed a constant now, then would I know that's not what the question asked, but if that field is now there forever and it's the same value, would that mean that C and D would be the same?
Wouldn't they all be zero?
They would all be zero. If the magnetic field's not changing at all, there's no change in the flux.
You're saying all of them, including outside of the magnetic field?
Yeah, because the only magnetic flux that's coming for all of them is based on what's in purple here. The magnetic flux in the middle of D is just this bit right here. In C, it's this part here. And for A and B, it's the whole purple circle.
So the based off that, the change in the magnetic flux would be greater when the area is greater?
Yeah. If my magnetic field, so if my magnetic field goes from 4 Tesla down to 2 Tesla, and my area, if I have a magnetic field that's going through an area of, say, 1 square meter, then I'm going from 4 Webers to 2 Webers. 2 Webers. If the area is 2 square meters that has this magnetic field going through it, then my flux is going from 8 Webers to 4 Webers. The greater the area, even though the change in the field is the same for both, the greater the area, the greater the change. This change is,
Oh,
that's change of -2, that's change of -4.
Oh,
So,
that makes sense.
so for all of them, the ratio of the change will be the same?
Ratio of the change. The ratio of what?
I guess for each, spot on that diagram, if the field changes and the area is the same, then the flux would decrease by this, like some constant or something, the same for all of them?
No, it's not, and the difference is that if every single one, if my magnetic field was this big, then yes,
Okay,
if I understood you correctly. But it's not that big, my magnetic flux is here. Because remember back when we were doing electric field, there was a problem where I had some sort of surface right here, I had an electric field that was different for half of it, for part of it. And so you basically did the flux for one half and then the flux for the other half and added them together. Same thing here, if I've got, make it a circle, I got a magnetic field through here and I have no magnetic field through this part, the magnetic flux through this open surface here would be the magnetic flux of this part, which is 0, plus the magnetic flux of this part. Well, the circle. So, in that case over there, it's only that small, that the purple circle or blue circle in the problem that is creating any magnetic flux at all.
What's EMF stand for?
Electric motor force, right?
That's where it started.
You said, no, it's not a force.
It is not a force. So what does EMF stand for now?
EMF.
Yes,
But it's not a force.
it is not.
It just stands for EMF?
Yep. It originally stood for electromotive force.
But then they
But
found
now
out it
it's
wasn't a
just
force.
EMF.
It's just EMF.
What's a good like layman's term that we can call that's correct?
Ideal voltage.
Ideal. What makes it ideal?
No internal resistance.
Sorry, to clarify, through the circuit? And no internal resistance through the circuit, or?
No, if I have a 12-volt battery, I'm not necessarily really getting 12 volts out of that.
Oh, okay.
Well, one, quality control, but also, 12 volts would be the EMF, ignoring any resistance within the battery itself.
So technically the two outer rings should be the same? Okay.
I thought you said the greater the area.
If they were all within a magnetic field that was getting smaller, then yes.
But then eventually the magnetic field comes to an end.
Yeah.
So the two outer rings will only get the aspect of the magnetic field that they're both a part of. So their area along being it greater than the magnetic field becomes irrelevant?
What was that last one? I was agreeing with you until the end, I missed.
Wait, so because both of those rings are bigger than the magnetic field, they both encompass the whole magnetic field, but that extra space that they have,
Contributes nothing.
okay.
So they do have the same rate of change in the electromagnetic, or the magnetic flux.
Yes.
So wouldn't the two inner ones have the same?
No, because they are encompassed by it, because the magnetic field's larger than they are, then it does become proportional to the area.
So it's proportional area so long as it's smaller or equal to that size of the magnetic field?
Ask that again?
It's proportional so long as it's smaller or equal to the magnetic field?
Yes. Other questions? Chance, you look like you want to ask something.
I'm still not seeing how there's any change in the magnetic flux if they're both completely engulfed in the field.
Field shrinking.
But you're saying,
Well, there's
but who's to say where the field is when I do the problem? Is what I'm confused about. Because like if we use the diagram there, they're both engulfed in the field. And the field's on the outside of them, so I don't get why the magnetic flux would be changing on the in ones, or the ones
Alright.
inside.
If I've got, let's say I've got a magnetic field coming out of the board, shooting magnetic arrows at all of us. So I got this. All right. Picture of the whole board dotted. And so that's a magnetic field. There's no flux through any surface because I haven't created a surface yet. So let's create a surface. So I've got a surface right there, and I want to figure out the magnetic flux through it. The only magnetic field that I care about is the magnetic field that's actually going to go through this surface. All of this other stuff does not matter at all to the flux going through this. So I'm going to get whatever the magnetic field is times the area of that circle. If I take a second circle, a bigger one, same magnetic field, but it's got a bigger area, so it's got a bigger flux. It does not care about this, it does, or anything outside of it. It only cares about what's inside. If I just move this circle so that it overlaps with this one, that doesn't change the problem. This still has a certain amount of flux based upon its area. Doesn't care about that one, its area in the magnetic field.
That makes sense.
So in the case over here, when I have them concentric like that, this has some magnetic flux going through it. This has a bigger magnetic flux going through it. I feel like I'm missing. Then try again.
I don't, if they both are in the magnetic field.
Right.
And it's still bigger than they are.
Yep.
There's no change in the magnetic flux. That's what I.
But there's change in the magnetic field, so there is a change in the flux.
It
What
takes,
is, what is changing in the field?
The field is getting smaller.
You mean the field is shrinking, or like the magnitude of the field?
Magnitude of the field.
Oh,
How do I word that? Uniform magnetic field directed out of the page, getting smaller. Ah,
Oh, so it's just, okay, the magnitude of the field.
yes. Sorry,
Oh, okay, that's what, I thought you meant it was.
yeah, now I see where you're coming from. Yeah.
Okay. Thank you.
All right, I need to obviously update that wording.
Thank you, that's, sorry, I was really confused.
Yeah, I can now understand your questions and why that would be confusing.
Okay, thank you.
Speaking of wording,
It would help if you would read my mind at times, it would really solve a lot of problems. Yes, speaking of wording,
unless there's no other questions for master set 32, for master set 33,
Uh-huh.
you have, I guess how I wrote the structure of the circuit, was an AC circuit in series with the capacitor, and then in series with those two is a parallel structure with a resistor and inductor. Is that
Uh-huh.
what you intended for us to draw?
yeah,
And then, I remember, so I was watching the videos and you were saying whatever you can, I guess, equate to each other to figure that out. So how would you find the capacitor voltage phasor?
all right. Let me do a different problem, but still one with, again, a series with a component and then a parallel structure.
Okay. And also, for AC, can we still use all of Kirchhoff's rules?
Yeah, we'll get into what you can and cannot use.
Okay.
Basically, I'm gonna put up a problem, we're gonna solve it two different ways. We're gonna solve it using the phasors, and then we're gonna solve it without phasors. There's definitely an advantage to without the phasors, it's just physics textbooks tend not to go that route. So, there we go. All right, so this is not gonna work here. So I've got my AC power supply, I have an inductor, I have, and then a parallel structure, let's extend it out like that. And I've got a resistor and a capacitor. Make this 150 ohms, make this 30 microfarads, and make this 400 millihenries. So numbers similar to the problem here, except I upped the inductance. So to start out with the phasor diagram, oh, and then let's not forget the rules. Things that are going to be true regardless of the setup is that X sub C, the capacitive reactance, is equal to 1 over omega C. The inductive reactance is equal to omega L, and then resistance is just resistance. I have Ohm's law variations. I know the voltage across the resistor is equal to the current across the resistor times the resistance. Then I've got VL is equal to I sub L, X sub L, and then V sub C is equal to I sub C, X sub C. And I will definitely try to make my L's and C's look different. I know that omega is equal to 2 pi f. I know that the peak value is equal to the RMS value times the square root. So let's start out with the phasors. Oh, so what we're trying to find here, really in order, in the end, I think it's, what are the 8 equations? I have current out of the power supply, current out of the inductor, current through the inductor, current through the resistor, current through the capacitor. And do that one again, lowercase. Current out of the power supply, current out of the inductor, or through the conductor, current across the resistor, current across the capacitor. And then I have voltage for the power supply, voltage for the inductor, voltage for the resistor, and voltage for the capacitor. So basically, we've got, those are the 8 equations I'm trying to find. Each of these equations has an amplitude and a phase shift. The angular frequency is going to be the same for all of them. So for example, IPS is going to be equal to some I, power supply, cosine of omega t plus phi of what phi is of IPS. So we'll find omega easily enough for all of them. And the numbers I used here in this problem, I went ahead and established epsilon sub naught is 300 volts. In the master step problem, I gave you an RMS value, and you just multiply times square root of 2 to get epsilon sub naught. And I also said the frequency for this problem here, I think it was 60 hertz in that problem, make it 50 hertz here. All right, so this is what we are trying to find. So for each of these, we need an amplitude and a phase shift. Now, like in the master set problem, I think I said, I established one of them. Yeah, draw the resistance voltage phasor at pi over 6. I'm gonna do the same for this.